Okay, so now we're going to be starting polyprotic acids and bases. So a polyprotic acid and a polyprotic base, what each of them is it's a chemical that will have multiple ionizations, okay? And the reason that we can tell if it will have multiple ionizations or equivalence points is based off of its charge or how many H's it has. So in this example, we have CO3 2-, which has a charge of 2-, which means it has the ability to accept or steal 2 hydrogens. That's going to show us 2 equivalents or endpoints on our graph, okay? Now, to start this example, we want to figure out what this graph looks like from 0 all the way through the process, okay, from the ground up. So it says of CO3 2-, that means we start with CO3 2- in our flask. With HCl means we are adding it. So if we start with CO3 2-, our initial pH is only based off of CO3 2-. Now, know that on the diploma, they might disguise this by putting a metal with CO3 2-. It might be like sodium carbonate. But just remember, you have to dissociate it, right? Whenever there's an ionic compound, dissociate it. Okay, anyways, we take that CO3 2-, which is an anion, which means it's a weak base, and we add water, okay? Because all that's in my solution right now is CO3 2- and water. Haven't added anything else. So this is my initial pH. These are going to combine, and they're going to give us HCO3-. The charge goes from 2- to 1-, and OH- because it's a base. Because it's a base, we're going to need a Kb value, which we get from doing Kw over Ka. Kw is 1.0 times 10 to the negative 14. And in this case, if we look at our data booklet, the Ka for the CO3 2- is 4.7 times 10 to the negative 11, giving us a Kb value of 2.12 ... times 10 to the negative 4, okay? Now, just because this is a weak base, and we've done this a million times, not actually, but pretty darn close, we're gonna make our ice stable. Products are always 0, they therefore go up, that means they're X. Initial concentration of carbonate is 0.4, it goes down 0.4 minus X. Awesome. Second step in our ice table process is we write our equilibrium law. So we take Kb from right here, and that is equal to our products over our reactants. Now, we don't like the minus X. So what do? We make an approximation by taking the initial concentration of CO3 2-, dividing by Kb, and seeing if it's over 1,000. Guess what? It is. And if it's not, assume it is. Go on with it. Okay? Our X goes away. We multiply both sides by 0.4 and square root. Okay? So, what that's going to give us, if we do some calculator punching, is an X value of 9.22 ... times 10 to the negative 3 moles per liter, which is X, and also our concentration of OH-. That's going to allow us to calculate our POH. But we don't really care about our POH, but we got to do it because it's part of our process. And that's going to give us a POH of 2.04. Now, we find that we don't want that, we want the pH, so we subtract 14 from the POH, and what we're going to get is 11.96. Okay, whew, we're speeding through it. So what that means, guys, is I go up to my graph, and at 11.96, which is just under 12, I'm going to throw up my dotted line. Not only that, I'm also going to ensure that I have a dot at the initial pH. Now, next thing we're going to do is our equivalence point. So, for our equivalence point, remember, the initial pH is just what you start with, and the equivalence point is when all of what you started with is gone, because you added something. And what we're adding here is HCl. But remember, HCl is a strong acid. So really, what we're dealing with is H3O+. Okay? So our equivalence point is going to be CO3 2- plus H3O+, giving us HCO3- and H2O. Now, I understand that there's two minuses here, which means that we should, or meaning that you could replace both of the minuses, but actually we're only focusing on the first equivalence point right here because there's two. And so because we're only focusing on the first equivalence point, we're only focusing on the first negative. Now, let's set up our molar coaster. Concentration of CO3 2- was 0.4. The volume was 25 milliliters. And the moles is C times V. And now the numbers are going to be different, like every other calculation. So we're going to get 0.01 moles. Okay, awesome. Now we're going to molar coaster it. Divide by 1 times by 1, because there's a 1-to-1 relationship. And the moles that we're going to get is also 0.01. Now, they told us in this example the concentration of HCl. And what we know is the concentration of HCl and H3O are the same because it completely ionizes. That concentration is 0.20 moles per liter. So to find the volume and over C, that's going to give us, with our fancy math, 0.05 liters, which is 50 milliliters. Okay, that is a little different than our previous examples, which were 25. So what we have to do right now is we got to change our x-axis. And you might have already seen this, but our x-axis before was 0 to 50. Now we got to go 0 to 100. Because at 50, I have my first equivalence point. So I'm going to go all the way up here. That's going to be equivalence point 1. Okay, step 3, final pH. It's the same. What have we been adding the whole time? HCl. So what do we end up with? HCl. Now we have to remember HCl is a strong acid, which means it ionizes 100% with water, which means they're going away to make 100% H3O and Cl-. And if the concentration of HCl was 0.2, therefore, according to our rules, the concentration of H3O is also 0.2, which means we can find our pH by doing negative log concentration of H3O, and the pH is going to be, drum roll please, 0.70. Okay, so I go to my graph, I take my meter stick, and I go just below 1. Again, it doesn't have to be super accurate, but good enough. And this is going to be my final pH, okay? Awesome. Now, let's go to the end point. But remember, because this is a polyprotic acid, base, a diprotic base, it's got 2 equivalence points, which means it's got 2 endpoints. But because we did the first equivalence point, we're going to start with the first endpoint. How do I do that? Just like we've been doing. Endpoint is pH1, or I, plus pH final over 2. That's going to be 11.96 plus 0.7 over 2, which is going to be 6.33. Okay. So I go over here, and I go to 6.33, and I draw a line. Now, remember, if we have a strong acid and a weak base, my endpoint is going to be below 7, and that is exactly what we see. So right here, we have end point 1, right? It is the pH of 6.33. Now, you're probably saying to yourself, sir, why did we just do that? This is what we've been doing every single time. How does it change for a polyprotic acid? Or you're just exhausted. Both are valid. Okay, this is the meat and potatoes. We're pretty much done everything. We just have to put a little garnish on it. Okay, put a little, bow. It's not hard. this is the hard work, and you've been doing it for the last couple days, so you're good. All we have to do now to figure out our second endpoint in second equivalence points is approximate. University will have you calculate it. High school, approximate it. And here's how we do it. If the first equivalence point, okay, was at 50 milliliters, if 50 milliliters neutralized half of what you needed, what would neutralize it all? Well, probably double, right? So all we do is we take our first equivalence point and we double it to get 100. Again, it might not be exact, but it's as close as we need to be. So it's an approximation. So our first equivalence point was 50, which means everything is going to be gone at double that, which is 100. So I go over to 100, and I draw my line, and I mark equivalence point 2. Now, guess how I'm going to find my endpoint? It's not going to be double, because that means I'm going back up. We started high, so we're going down. If my first endpoint was 6.33, in order to figure out what my second endpoint is going to be, it's going to be approximately half. So what is 6.33 divided by 2? It's 3.165, so let's call it 3.17. It's half, or approximately. So I go over here, and I go to 3.17, and I draw a dotted line. And boom, I have my second equivalence point. Now, what we need to do here is we need to sketch out our final graph. This is where it gets a little tricky. So you guys know that as you add stuff, nothing much changes, but then all of a sudden we have a sharp drop, okay? Nothing changes yet. We still have that sharp drop. But what we also have to end up with is going through this point. So what happens is once you hit that, your pH stabilizes. And then it drops again until you reach your final pH. And if you look at it, we have 2 sharp drops, which means we have 2 end points. We have 2 neutralizations. We have a first neutralization, but sorry, not misspoke, but we'll use a different word. We'll call them equivalence points. We have 1 equivalence point, which is our first sharp change in pH, and then we have a second one. And the reason we have 2 is because we have a charge of 2 minus. In the next example, instead of using a base, we're going to use an acid. So instead of having a charge of 2 minus, acids have hydrogens. So how many hydrogens do you think this could have?